All right, welcome everybody. We are going to get started now with our exam review for the final. You made it. It's a tough course, especially over the summer, but I think you've all survived well. Dr. Garg is a great teacher. So he explained it well. I've sat in lectures for other professors teaching organic chemistry, and it is not pretty. So be grateful that you all have Dr. Garg. So let's go ahead and get started here. So this is an overall review of Organic Chemistry 1, but we're going to focus on the chapters that Dr. Garg said he's going to focus on for your final exam. And so there's going to be a couple of questions on most of the topics covered, but don't use this as your study source. This is just to remind you of some of the topics that you might need to study a little bit better or refresh your memory on before you come to the final exam. So if some of this is kind of tough and you think, wow, I need to study that again, go to those sections in your notes, go to the book, get some more examples, and use this as kind of a guide to tell you what to study versus using this solely as your study material. Okay. So we're going to write the electron configuration for the following atoms. Does anybody remember how to do this? What do we start with? Atomic number, perfect. So what is the atomic number of chlorine? 17. So what column is chlorine in? So there's a total of 8 columns that we focus on. Does anybody remember? Perfect. Yep. It's in the 7th column. That means that we have 7 valence electrons or 17 total electrons. Okay, so that's a number to focus on. But what does this chlorine ion tell us? What does that negative charge mean? Perfect. It gives us 1 more electron. That's exactly right. Okay, so total we need our electrons to add up to 17 plus 1 because of the negative charge on there. So we need a total of 18 electrons that we're going to account for. Okay? So we start off with 1s2, 2s2, and we go 2px2, 2py2, 2pz2. Okay, so now we've accounted for 2, 4, 6, 8, 10 electrons, and we need 8 more. So let's carry on. We're going to have 3s2. Now we need 6 more. Okay, so now we're going to go 3px, 3py, 3pz. All right. Are all 3 of these going to be completely filled, or are we missing some? Completely filled. Perfect. All right. So that's how we do the electron configuration for that. Awesome. Now we need to do sulfur. What's the atomic number for sulfur? (16). Perfect. So we need to account for a total of 16 electrons. So what I'm going to do here, I'm going to write a quote so we don't have to do the whole thing again, okay? And I'm going to use that whole thing all over again. So we're going to skip ahead to the 3p shells, okay? 3px, 3py, and 3pz. Okay. So in our quotes, how many electrons had we accounted for? We've got 2, 4, 6, 8, 10, 12. So we need 4 more electrons, okay? And how we fill these p orbitals is we go one at a time, filling up px, py, pz, and then if we have extras, we go back and add a second one to each of those. So we have 4 more, so we're going to go 1, 2, 3. But because we have 1 more than we need to account for, 3px is going to be 2. So it's all the same that's in the quotes, 3px2, 3py1, 3pz1. Does everybody understand that? Any questions on how I got that? Awesome. We're going to calculate the formal charge for the following molecule. Okay, a little key there. Okay. It's pretty obvious to tell where we need to add formal charges here because they're boxed in red. I apologize. I use the same drawing tools you guys do for your homework, so I'm limited to that. I couldn't make it less obvious for where the charges needed to go. But let's figure out what the charge is on this carbon. Okay. To calculate formal charge, you want to do how many bonds something wants minus how many electrons it owns. Okay. So how many bonds or electrons does carbon want to own? 4, perfect. So we have 4. And how many does it own right now? Well, let's go ahead and count them. It owns these 2 lone pairs, so we're at 2. It owns one of the electrons in this bond, one of the electrons in this bond, and one of the electrons in this bond. So that adds up to a total of 5. So we're going to do 4 minus the 5 that it owns. That gives us a -1. So the charge on this carbon is a negative charge. Okay. How many bonds or electrons does nitrogen want to own? 5. Perfect. Okay. And that comes down to also the column that it's in as well. Nitrogen is in the 5th column. Carbon is in the 4th column. So that's how you tell how many they want. Okay, so it wants 5, and right now it owns 1, 2, 3, 4. So 5 minus the 4 that it currently owns is a +1. So that means the positive charge on that nitrogen. So what is the formal charge overall for the molecule? Neutral. Perfect. Net charge of 0. Awesome. All right, let's carry on. So we want to draw at least 2 resonance structures for the following molecules. Okay. So I'm going to start with how I like to do resonance structures is I say, all right, what's unhappy in this molecule and how can I fix it? So we have both a positive and a negative charge in this molecule. So that carbon that's positive and the nitrogen that's negative, those are both unhappy. No atom likes holding a negative charge or a positive charge. Okay. Some of them are better at doing so than others, but none of them like holding charges. Okay. So let's go ahead and think about what we could do to alleviate one of these, okay? There's lots of different options here, but I'm going to go ahead and just start with this, okay? I'm going to say, let's move this double bond up here, okay? So then that leaves us with a double bond here. This is our nitrogen. Our double bond here. And where does the positive charge go now? Bottom left carbon, you nailed it. Okay. Awesome. Okay. So again, we look at this and we say, what's unhappy and how can we fix it? Well, now the nitrogen's unhappy and the carbon's still unhappy, but let's go ahead and move these electrons onto here and form a double bond. That would give us okay. And now both the nitrogen and the carbon are happy. Awesome. So there's two resonance structures of that molecule. Another way to do this is to say, well, we can move these electrons onto here, and then that would automatically kick that bond up there. Okay. Lots of different ways to do that one, but we'll go with that answer for now. Okay. I think on my key as well, I drew a different way of doing it, so you guys can check that out as well. Any questions on that? Excellent. Okay. So now we look at the second molecule. What's unhappy and how can we fix it? Well, that carbon has a negative charge on it, so that's not going to be very happy. All right. So in order to be negatively charged, this carbon has to have a set of lone pairs. So one way to fix this or to resonate this negative charge is to move these electrons onto here and form a double bond. And then that would break the octet for this carbon. So we need to kick off that double bond as well. Does everybody see why that would break the octet for that carbon? Now to do a second resonance structure, another way we could do this is say, well, okay, here's our electrons that make that carbon negative. Let's go the other way with our electrons. Let's put them onto this side, okay? So then that would create sorry. So now we'd have a double bond here, okay? But moving the double bond onto there would break the octet. So let's go ahead and move the electrons out onto that carbon. So we'd have a negative charge here. Okay, so that's another way to draw a resonance structure. Any questions on these before we move on? Awesome. So we want to write the hybridization, the geometry, and the bond angles for the following molecules. So for this first one, we're going to be concerned about this nitrogen right here. First of all, what's missing on that nitrogen? Lone pair, perfect. This nitrogen does have a lone pair. So what is the hybridization for this? sp3, perfect, okay. It's got 4 regions of electron density around it, so that makes it sp3, perfect. Now, what is the geometry? Does anybody remember how to do this one? Trigonal pyramidal, perfect. That's something you just got to memorize. You got to know if there's 3 bonds and in one set of lone pairs, it's going to be trigonal pyramidal. How about our bond angle? 107. Perfect. And how do we know that? Does anybody remember my trick? (109 minus 2), perfect. Okay, so my trick is to say on a regular tetrahedral, right, if you have a carbon with 4 things around it, the bond angles are 109.5. And so when you take away one of these bonds and add a lone pair, there's 2 electrons. So you can take 2 away from 109.5 and get 107. Just a little memory cue there. Hope you remember. Perfect. All right, and how about for this carbon right here? What is our hybridization? sp2, excellent. sp2 because there's 3 regions of electron density, so sp2 for the 3 regions. Perfect. How about our geometry? Trigonal planar, perfect. Okay. The reason it's called planar is because it's all on one plane. There's nothing going forward, backward, up, down. It's all on one plane. Okay. Trigonal planar, you can remember that. And then what is our bond angle? Perfect, 120 degrees, okay. You can kind of picture it, right? 120 degrees for each of these. Those 3 add up to 360. So that'd be your total circle. Awesome. All right, so we want to complete the acid-base reaction below. Okay. So what's our acid here? Is it going to be the left or the right? Perfect. We have acid. And this will be our base. Acid-base chemistry, what happens first? Feel free to unmute yourselves as well if you want to talk. The oxygen takes the hydrogen from the acid. Perfect. Which hydrogen is going to be this one or this one? Left or right? Yep, the right one. Perfect. Okay, that's our more acidic proton here. The reason it's more acidic is because when you take that hydrogen, then it can resonate that negative charge. Okay, so our oxygen is going to steal this proton, and then the electrons between the oxygen and the hydrogen are going to go onto the oxygen. So our product here is going to look something like this. This is our conjugate base, conjugate acid. If I told you that the pKa was 3.7 here, and the pKa was 19. Is this reaction going to prefer reactants or products? Products, perfect. So our bigger arrow is going to go towards our products. Okay. Perfect. All right, let's name the following molecules. So what I like to do for these is I like to go through the whole molecule and label, name all of my substituents. Okay. So let's start with this top one. What is this substituent at the top called? Anybody? This is a sec-butyl. Okay. Now this group right here. Isopropyl. Here we have a methyl. ethyl, and tert-butyl. Awesome. Kind of a tricky one here. What do you think is going to be our number 1 carbon in the ring? Yep, perfect. Okay, and then we number to keep our substituents on the lowest. Okay, so we wouldn't want to go this way because then our substituents would be on high numbers. If we go this way, the substituents stay on lower numbers. Okay. So now we want to go in alphabetical order. Okay, and put it all down. So we're going to start with sec-butyl. What comes next? Right, our tert-butyl. Sorry, that needs to be 5. 5 tert-butyl. Next is our ethyl. 4 ethyl. You need to put 1 sec-butyl. That's optional. Yep, you do not need to put 1 sec-butyl because when we don't put a number, they assume it's on the first carbon. Okay. So we have our 4 ethyl, then 2 isopropyl, then 3 methyl. What's our parent chain? Cyclohexene. Perfect. Very long name for a very complicated looking molecule, but if you just take it slowly, look through, make sure that everything is lined up exactly how you need it, you'll be good to go. Nothing too crazy. All right, let's do this next one. We have a symmetrical molecule here, so it doesn't actually matter which way we number, left to right or right to left. I'm just going to number this way. Okay. We have a 4 methyl. We have a 2 sets of ethyls. Okay. So what are we going to start with first here? Okay, our ethyl is going to be first. We have a 3,5 diethyl, 4 methyl. And what's our parent chain? Heptane. Beautiful. Good work, guys. Okay. Any questions on either of those? Moving along. So I want to label our stereocenters as R or S. So here we have to choose priority groups. So our oxygen is obviously going to be our number 1 over our 3 carbons. And then our shortest carbon chain is going to be the least highest priority. Okay, so we can go ahead and label this as number 4 because that's our shortest chain. Out of these 2 carbons, which one is a higher priority? Left or right? Right, perfect. So this is our number 2 and our number 3. The reason for that is that if you write the 3-letter codes for both of these, this 3-letter code is carbon, carbon, hydrogen because of these 2 carbons. The 3-letter code for this carbon is just carbon, hydrogen, hydrogen. Okay, so that's our higher priority is the right side. Perfect. All right. So our number 4 is already going to the back, so we can just determine straight away if it's R or S. This is going counterclockwise, so is this R or S? S, perfect. If you notice, when you start to write the letter S, it goes in a counterclockwise motion and then finishes off that way. Okay, so that's how you can remember S is counterclockwise. All right, again, R or S for this one. So we have 3 oxygens and a carbon, so our carbon is going to be our number 4. What do you think our lowest oxygen is going to be? Right, left, or bottom? Left. And mind blown, Tony, I like it. I like to blow your guys' minds. Good way to remember it, okay? So Tanner says left oxygen. So this is going to be our lowest priority. Not quite, okay. That is our highest, perfect. So this oxygen is our number 1, perfect. Okay. And then this one is going to be our lowest oxygen, okay, because it doesn't have a carbon chain. And then this is our number 3. Sorry, number 2. Okay. So now we have to say, well, our 4 isn't moving to the back. So we have to change that. Make sure our number 4 is facing the back. So we're going to swap our 2 and our 4. So our 4 is going to the back, and we'll keep 3 and 1 the same. So this is pseudo what? Pseudo S, perfect. So that means the original is R. Awesome. And again, a little memory trick here. When you write the letter R, the curved part of the R goes in clockwise direction. So that's how you can remember R is clockwise. A little hint there. Another mind blown, Tony. All right. So now we want to, oh, let's see. No, I ended up getting rid of this problem after I sent it to you guys. This is a really bad example. All right. So we're just going to ignore that one. Let's see, isn't there another stereo center on that? Technically, this would be a stereo center, but I didn't give you any more information, which one's going forward and backwards, so we can just ignore that for now. Okay. And then this one was a really bad example, but let's do another similar question, okay? So if I were to draw this molecule, this ethyl group right here, is this going to be up or down? Up, perfect. Up and what, axial or equatorial? Axial. Beautiful. And then our tert-butyl group over here is going to be up and equatorial. Okay. So now we want to do a chair flip. Okay. And then we're going to determine which one is more stable. All right, so we're going to do a chair flip. All right. So our tert-butyl group, what changes on these? Is it up and down that changes or axial equatorial? Axial equatorial, perfect. So our tert-butyl group needs to remain facing up. Okay. So how you draw up on the 4th carbon is like this. Okay, so that's still up, but it is now axial. Okay. And then our ethyl group on carbon 1 needs to remain facing up. Draw that a bit better. Okay. But it is now equatorial. Okay. So which one of these is our major contributor, or which one is more stable, left or right? Left, perfect. More stable. How so? What makes it more stable? The bigger group is equatorial. Perfect. Our bigger group, the tert-butyl, whoops. Our tert-butyl group is equatorial. That makes it more stable. Okay. All right, so I actually stole this problem directly from, I think it was our exam 2 review that I did, but I wanted just to bring it back to make sure that we're kind of looking at all of the, different things we can look for here, okay? So what would a alcohol group show up as? Feel free to unmute yourself as well, if that's easier. What does it show up as in our IR spec? A broad signal, perfect. And it shows up somewhere around here, right? Around 3,300, perfect. Yep, somewhere between 3,000 and 3,300, something like that, but it's a broad peak, okay? So we know it's not C or D. So now we're looking for the difference between A and B. Really, the only difference is the ring. So how are we going to determine the difference here? How do we know which one it is? Perfect. Yep. The fact that there's sp2ch bonds, okay, those are going to be your hydrogens on the ring. Okay. The other way to tell is the 1600 is C double bond Cs, and there are none of those in answer B. Okay. So it is A. Okay. Let's carry on to this next one. Okay, anything of particular importance in our IR spec? Okay. So we've got just over 3,000 here. We have sp2. Okay, so we know there's going to be a double bond of some sort. Is it pretty small for you guys? Yeah, it's blurry. Sorry. Does that help? Not really. Okay. Well, hopefully it makes more sense on the key, but you can't see the numbers. That's all right. Okay, so here's our 1500 mark. So we've got a little peak here we need to look at, which is C double bond C, and we know there's sp2, so that's going to give us our C double bond, or our double bonds, okay? sp2ch bonds. All right. So then we have our mass spec down here as well. What do we know is in this molecule? Bromine, perfect, okay? And that's because we have an M+2 peak, and it's at a 1-to-1 ratio. That tells us that there is a bromine, perfect. And our molecule is gonna weigh 120. Okay, let's put all the pieces together. I apologize for the blurriness, but we know we have a bromine, okay? We know we have a double bond. We know the mass is 120, all right? So let's go ahead and add up all of our things here. So we can start with bromine. Bromine weighs 79 grams per mole. Okay, so we're just going to add that in. Carbons, let's guesstimate how many carbons. How many carbons do you think will be in this? We're already at 79 with our bromines. We need to get to 120. So let's guess 3. Okay, so that would be, they weigh 12 each. So that would be 36. And then we're not sure how many hydrogens, okay, but we need to add up to 120. Okay, so let's go ahead and try to draw our molecule, okay? So we have 3 carbons in a bromine, and we know there's a double bond. Okay? And in this structure, we'd have 2, 3, 5 hydrogens. Okay? Okay, so they weigh 1 each, and there's 5. Okay? And that does check out to our 120. Okay, let's make sure that everything else lines up. Okay. We had our bromine added up to 120. Our IR spec said that we had C double bond and sp2 CHs. So it looks like everything checks out, and that's our structure. Any questions on how I got that one? Awesome. I apologize, we got one more blurry one. I'm sorry. Okay. Well, what's pretty prominent here in this IR spec? What do we see here? Okay, it looks like an OH. It's very similar to OH, but it's a little bit further down. It actually goes through 3,000. Okay, so we have a super broad peak that goes through 3,000. Not quite, you're close. It looks like it. Yep, it is an acid. What type of acid? Not a ketone. Anybody remember? Carboxylic acid. Perfect. Okay. When you have a broad peak that goes through 3,000, you're going to have a carboxylic acid. Okay. And then there's not a whole lot in here, but that's 1,600, so we know that's a C double bond C. I apologize for the blurriness. Okay. So we know we have carbon-carbon double bonds, and we have a carboxylic acid. That's what we pull from our IR spec. All right. Awesome. What does this one hydrogen that's above 12 tell us? Okay. I don't know if you can see that, but this number right here is 12. Does anybody remember what that proton is? There's only one type of proton that's that deshielded. Anybody remember? It's a tricky one, I know. It's actually our carboxylic acid proton, okay? So the only type of proton that's deshielded beyond like a 10, right, is our carboxylic acid protons, okay? So we know this is our acid proton, okay? Between 6.5 and 8, what are these 4 hydrogens telling us? And you are going to have this on, you'll have the key on your exam, right? He'll tell you, what to look for, but perfect, Tanner, we have a benzene ring. What type of benzene ring? Disub. Okay, we have a disubstituted benzene ring, okay? So there's 4 protons, 4 hydrogens. So we know we're going to have a benzene ring that has 2 things on it, okay? Disub, because our 4 protons are these 4 right here, okay? If there was 5, would it be mono? Exactly, perfect, Lynn. So if there were 5 protons here, first of all, there would just be 1 peak. It would be like that, okay? And it would say 5 protons. Yep, and then that would be mono substituted. Yep. Okay, so we know it's disubstituted. we have a carboxylic acid that we still need to account for. So let's go ahead and just add a carboxylic acid onto one of these. Okay. And then what do you think this 3 hydrogens with no neighbors are going to be? A methyl group. Perfect. So this is actually our structure right here. Do we have any questions? I'm here for you guys right now. Anything you need, any questions on these? All right, carrying on. So now we're going to move on to substitution reactions, okay? And I believe, as far as what I understood from Dr. Garg's announcement, is that he's going to focus on substitution and elimination reactions for the exam. You're obviously going to have other topics, but I would really make sure that you understand these, okay? And also, not only because it's going to be on your final exam, but SN1, SN2, E1, and E2, that's basically all you do for OChem 2, all right? It's just variations of substitution and elimination reactions that kind of go all the way through OChem 2. That's what you're doing the whole time, all right? So get used to these, get used to seeing the patterns here. All right, so here's a little summary table that I drew up. I added this to your last exam, okay? But I wanted to bring it again. I used this, I kind of went into my exam and I immediately wrote down this chart. If that's how your brain works, great. If not, ignore me for the next minute or so. But I was just able to go into my exam. I pretty much had this table memorized, and I went in SN1, 3 degree, 2 degree, rate, 2 steps, protic solvents, weak nucleophile, 2 products, right? I just wrote that whole thing out. Same with SN2, wrote all the things. Okay, and then when I got to the substitution reactions, I was able to look through this chart and say, okay, what do I have here that tells me which one it is, and how do I know what the answer is going to be? Okay, so that's my personal way of doing it. You guys decide how you want to work through these, but this chart really helped me. Okay. So let's start with this first one. What is the SN2 product between S2 bromopentane and the hydroxide ion? Okay. So first we need to draw S2 bromopentane and the hydroxide ion. So we know we have a 5-carbon chain because it's pentane. Okay. And the bromine is on the second carbon. Oops. All right. But it needs to be an S configuration. All right, so we're going to go ahead and guess here. I can't remember for sure right now, but let's go with a wedge, okay? And let's see if that gives us S configuration. So our bromine is obviously going to be number 1. Our hydrogen is going to be number 2. Sorry, number 4. Okay, and then the longer carbon chain is a higher priority, so this is 2 and 3. So right now, we don't have to move our 4 to the back, it's already in the back. And right now this configuration is R. Okay, so we guessed wrong, that's okay. We go back and we say, okay, we know our bromine is on dash. Okay. And we can double check that by saying, okay, our bromine's number 1, our hydrogen is number 4, number 2, number 3. Okay, we need to do a pseudo, it would be pseudo R, which means our original is S. Okay. So that checks out there. We know this is S. And then we have our hydroxide ion, which is just OH minus. Okay. We know it's SN2. Okay. So what happens in SN2 to stereocenters? Anybody remember? says it right here. We have inversion of stereochemistry, okay? So what happens is because SN2 happens in one step, okay, your nucleophile, your strong nucleophile, okay, this is how it all comes together. Your strong nucleophile is able to come in and attack from the opposite side of your leaving group, and then your leaving group leaves, okay? And so then you're going to get your inversion of stereochemistry because it attacks from the opposite side. So our bromine was going away from us, so the hydroxide ion is going to attack towards us, right? Or facing towards us. So that's how you know that's how that works. That's how it all comes together. We get a bromine. Any questions on that? Okay. So we need to determine if the reaction will be SN1 or SN2, determine a good solvent, and then draw the products. Okay. So first of all, what's our alkyl halide in this first one? Is it primary, secondary, or tertiary? Tertiary, perfect. Okay. Because it's attached to this carbon, which is attached to 1, 2, 3 other carbons. Okay, so it's tertiary. All right, so straight away, we know this is SN1 or SN2. SN1. And here we have a weak nucleophile, which is another indication that this is a SN1 reaction because it prefers SN1. What type of solvents is SN1 like? Protic or aprotic? Protic, right? H2O, any type of protic solvent. Okay. You do H2O, it could be, you know, OHCH3, something like that. Anything that has a proton, okay? Protic solvents. All right. So now we need to determine the products. I'm going to start with this, okay? And what happens with SN1s as far as the products go? Is there 1 or 2 products? 2, right? Perfect. So what does that mean for this problem? Okay. We're going to have a racemic mixture of 2 different products. So what's going to happen is on one of them, our methyl group is going to get pushed to the back and our OCH3 is going to attack from that side. What's also going to happen in some instances is that our OCH3 will attack from the back and our methyl will be pushed forward. Okay, so we have 2 products and they create a racemic mixture. Top and bottom attack, perfect. All right, so let's do this next one. We have a strong nucleophile and a 1-degree alkyl halide. So what does that tell us, SN1 or SN2? Man, you guys are on to it. SN2. Perfect. Okay, so we have a strong nucleophile. We have a 1-degree alkyl halide. Okay, so SN2. We want an aprotic solvent now. What type of aprotic solvent could we use? Acetone, that's fine. Could be DMF, DMS, could be another type of aprotic solvent, okay? If he ever asks you for an aprotic solvent and there's letters, it's gonna be sorry, if he ever asks you what type of solvent it is, protic or aprotic, and there's letters, it's going to be an aprotic solvent. Okay, so just a little hint there. Okay, acetone could use DMF, anything. Okay. And then what happens with SN2 with stereochemistry? Inversion, right? Unfortunately, there's no stereochemistry on this one. Okay, so there's only going to be one product, and it's going to be this right here. So our OH attacks that carbon, and the leaving group leaves. If you were to draw out the full mechanism here, then, well, yeah, that's technically the full mechanism there. In our SN1, the leaving group leaves first, and then you get a carbocation intermediate, and then the nucleophile attacks, but we don't need to worry about mechanisms right now. Cool. All right, again, we've got strong or weak nucleophile here. Anybody know? Anytime you see a charge, okay, it's going to be a strong nucleophile. Okay. Strong nucleophile. Okay. Tanner, jumping a little ahead. It is SN2, okay, because we have a strong nucleophile. And this is a 2-degree alkyl halide, so that could be SN1 or SN2, okay. No, you're good, Tanner, you're good. All right, so that is SN2. We have a strong nucleophile with 2-degree alkyl halide, okay. SN2 likes what type of solvent? Aprotic, so let's go with DMF, right? Any type, doesn't matter. Okay. So now we have this product. With SN2, we have inversion of stereochemistry. So right now, in the original, the bromine is facing down. So which way is our nucleophile going to attach? Up or down? Nucleophile is going to attack up. Perfect. We have this right here. Okay. And our terbutyl is going to remain the same. It's not to proportion, I apologize, but cool. We also have again, you got to make sure that you watch out for that SN2, that there's inversion of stereochemistry. So if it's at a stereo center, it's going to have an inversion. Okay? Keep an eye out for that. All right, so on this one, we're kind of working backwards. I want us to determine what nucleophile we're going to use in order to get this product. Okay, first of all, what degree alkyl halide do we have? 1 degree, right? Primary. So we know this is going to be SN1 or SN2? SN2. Okay. SN2 wants a strong nucleophile. So our nucleophile is what gets attached to our molecule. What looks like it gets attached? Right? Well, we have a whole new ring in here somehow, right? And we have an oxygen, okay? So it's going to be everything attached to the oxygen onward. So we have oxygen attached to a ring, okay? And we wanted a strong nucleophile. So should we add a proton to this or should we leave it negative? Leave it negative. Perfect. Awesome. And what type of, let's just go with DMSO. Doesn't matter, any type of aprotic solvent. Awesome. All right, on to elimination reactions. Okay. So this is the new stuff, and we're actually going to have plenty of time for this topic, so I'm happy to answer any questions, give you plenty of examples, whatever you guys want. If you feel comfortable at the end of these, we'll call it good. If not, I'm happy to stay around for the next little while, but let's get through these couple of problems that I gave you and then see how we're feeling, okay? Again, I provided a little table here. Not as helpful as the SN1, SN2 table, just because some of the E1, E2 rules kind of apply on both sides, okay? Obviously, you have weak base for E1, strong base for E2, 2 steps and 1 step. And the rest of it, I mean, kind of just depends on the situation, okay? What's going to happen with each one and how it's going to go, okay? So those are kind of the most important things there. Strong base, weak base, 1 step, 2 step, okay? So we have a 3-degree alkyl halide here, okay? So they're both gearing ready to go, okay? I had a question, can we go over the elimination worksheet posted? I'm more than happy to do that at the end of this, okay? Let's get through these couple of problems and then I'll hop over there. Okay. So, first of all, is this a strong or weak base? It is strong, okay? Because potassium likes to separate. Okay. Potassium is one of those that is totally happy holding that positive charge, all right? He's very content. It's almost as if he's positively charged and the OH is negative. Not quite, but it's very close, okay? All right, so we have a strong nucleophile, or strong base, sorry. So what is that gonna be? E1 or E2? E2, right? Because we have a strong base. Perfect. Okay. So now we need to look at, is this a bulky or a small base? Kind of the trick here is to say if there's more than 4 carbons, okay, then you know that it's going to be a bulky base. 4 or more, okay? But we have quite a small base here, so small base, okay? That's going to be key for telling us our major and minor products. Did he talk to you guys about major and minor in elimination reactions? I don't want to go over it if he didn't tell you. He did go over it. Perfect. Okay. So we do need to talk about it. All right. So what happens in elimination reactions? Is anybody comfortable enough to unmute themselves and kind of tell me the process of what happens? If not, no worries. Okay, elimination reactions, okay? So what happens in these is a base of some kind, okay, steals a proton from the molecule, and because the molecule then becomes negatively charged, okay, it wants to not hold that negative charge, and so it gets rid of any leaving group it can and forms a double bond. Okay, that's essentially what happens in an elimination reaction. A base steals a proton, and then the molecule becomes negative, and it gets rid of that negative charge by forming a double bond and kicking off a leaving group. Okay, That's the basis of elimination reactions. Okay, so our base molecule here is going to look the same. We've got 2 methyl groups here. We got this methyl, okay. But our bromine is our leaving group, okay? So now we need to determine where on Earth this double bond can go, okay? Did he talk to you guys about the alpha carbon here attached to the leaving group? Okay, we label this as our alpha carbon, okay? The carbon that's attached to the leaving group is our alpha carbon. Then we have beta 1, beta 2, and beta 3. Okay. One of these, beta 1, 2, or 3, cannot accept the double bond. Which one is it? Does anybody know? It is number 2, okay? Because there is no proton to abstract from that carbon, okay? You guys have it exactly right. There's no proton to extract from that location, so beta 2 will not have a double bond between alpha and beta 2, okay? So now we draw our 2 products with double bonds between alpha and beta 1, alpha and beta 3. Okay, so we can draw that one, and we also have this product here. Okay. And the reason it's able to do that is because the base steals a hydrogen from those carbons, and then that negative charge that's on that carbon flips down and forms a double bond, okay? And then that kicks off our leaving group. All right, so because we had a small base here, which product, A or B, is our major product? Does anybody remember the rules here? It is A. Okay. This is our minor. All right. And the reason for that is because with a small base, okay, it's what's called the Zaitsev rule. Okay, it's going to want to go to the more substituted side. Okay, so is this double bond right here, is it mono, di, tri, or tetra substituted? Does anybody know? It is tri substituted. Okay, there's 1, 2, 3 carbons on either side of that double bond. Okay, now I know we're getting kind of thick here. Okay, but just stay with me. This double bond is tri-substituted, whereas this double bond is only di-substituted, okay? With a small base, the major product will be more substituted, the more substituted double bond. Okay? That's the Zaitsev rule, okay? And did he talk to you guys about how to remember that? Did he tell you his little trick to remember that? Okay, here's a trick. Zaitsev kind of sounds like a dweeb, right? He sounds like he's not very strong, okay? So Zaitsev, he wants to get stronger. He wants to bulk up. So he wants to eat more subs, okay? He wants to eat more subs so he can bulk up. Hoffman, on the other hand, he sounds like a big burly dude, okay? So he needs to trim down. He needs to eat less subs, okay? So the small product, the small guy, is Zaitsev, and he's going to go more subs. He's going to bulk up and eat more subs. Hoffman, if we had a bulky base, okay, it's going to be a Hoffman product is going to be your major, and Hoffman needs to go less subs because he needs to slim down a little bit, lose some weight, okay? I'll give you some more examples of those, but that's just a little memory trick there, okay? So we had a small base, so that's Zaitsev, and our major product is the more substituted. Okay, just a little way to remember that. Hoffman is bulky, Zaitsev is not bulky, he wants to bulk up. Okay. I hope that makes sense. I'm not getting much feedback today. All right. So next, we have our alpha carbon. Okay. We have potassium tertbutoxide. This is a very common base that Dr. Garg likes to use. Okay. It's exactly what it sounds like. It's a potassium attached to a tertbutoxide. Okay. Tert obviously is a tert-butyl, and oxide is a negatively charged oxygen. So we have an oxygen attached to a tert-butyl. Okay. And here we have 4 carbons, so this is considered a bulky base. 4 carbons is considered a bulky base. All right. So bulky means what? Zaitsev or Hoffman? It's a bulky base, so it's going to go Hoffman, so we want the less substituted product. Okay. All right. So now it's going to happen. We have our beta 1 and beta 2. Which one's going to be our major product? The double bond between beta 1 and alpha, or alpha and beta 2? Any thoughts? Since it's Hoffman, I want to go less substituted. It is not the same. Okay. It's actually, yeah, it is beta 1. Perfect. Because beta 2, if we had a double bond right here, it would be tri-substituted. If we have a double bond right here, it's going to be di-substituted. So the chlorine will leave and that double bond will be di-substituted. Perfect. You got that exactly right. Okay. So we're going to have our chlorine leaves. And our major product is with the double bond there. Any questions on that one? Okay. Cool. Carrying on. I forgot to write that this is an excess. Okay, we have excess in NH2. Okay. Now this is a little bit of a tricky one. With excess NaNH2, does anybody know what it does for elimination reactions? Did he go over this one? Okay. Excess NaNH2, any proton giving, right? Because NH2 is very proton giving. That's in excess is going to take all leaving groups down to double bonds. Okay. So what's going to happen here is we're going to get both of those bromines are going to leave, and we're going to get a triple bond right there. Okay. That's just a little hint right there. I'm not sure if he's going to go over that for the exam. It sounds like nobody was really aware of that one, so he may not do that one, but just be aware of it, that if there's a proton giving molecule in excess, Okay, it's going to take all of your leaving groups down to either double or triple bonds. Because there was 2 leaving groups here, we got triple bond. If it was just one of the bromines, then you would get a double bond there. Okay. All right. And last one that I brought. Okay. We have a strong and a small base. Okay. We have our alpha carbon, beta 1, beta 2, beta 3. Okay. Any of these that the double bond can't go between? Any of them not able to do an elimination reaction? Beta 1? No, beta 1 is able to do it. It's got a proton. Okay. So it looks like all of them are because they all have protons. Okay. So we're going to get one of the products is going to have a double bond here. We're going to have another product with the double bond here. We're going to have another product with the double bond here. Sorry. Not there. Here. There we go. I was like, that doesn't look right. Right there. Perfect. Okay. So this is our beta 1 product, beta 2, and beta 3. Okay. So we had a small, strong base. We have a small base, Zaitsev or Hoffman. Zaitsev is a small guy. He wants to bulk up, so he wants the most substituted product. So what do we think is going to be our major product? Beta 1, beta 2, or beta 3? Beta 2, perfect. Okay, because this is tetra substituted. It's got 1, 2, 3, 4 carbons on all sides of its double bond. So that means that it's going to be tetra substituted. And that's going to be our major product. Awesome. Okay. Any questions? Okay. Well, everybody feel free to leave at this point if you'd like. It sounded like some of you wanted me to go over the worksheet for elimination reactions. Is that still what you guys would like me to do? I'm going to do an E1 example. Sure, I can do that. Okay. Let me try to think of one here. All right, so E1 will be something like this. See if this works. Yeah, that should work. Okay. So we have a weak base, and we have a small base. So he's weak and small. This is going to be E1 because we have a weak base. The rest of them I did were strong, huh? Yeah, perfect. Okay, so this is a weak base. And because it's small, is it going to be more substituted or less substituted double bond? More substituted, perfect, okay? Because Zaitsev is small, Zaitsev wants more substituted, okay? So we're gonna get this product. Did you guys want me to draw the mechanism for this, how it works? Perfect, okay, I can do that. So what happens is, if you look at a water molecule, it's shaped like this, right? So our oxygen is gonna come in and strip one of these hydrogens, and the electrons will go onto this carbon. So you'd be left with this, right? And then what happens is the electrons go and form a double bond right there, and that kicks off our leaving group. So then you get our product. So that makes sense to everybody? So Zaitsev and Hoffman apply to both E1 and E2, or just E2? Both. It's for both. Okay. So our water molecule steals a hydrogen, we get a negative charge, and then the negative charge forms a double bond, kicking off our leaving group. Okay. Bromine is pretty happy holding a negative charge, so it's fine leaving with that negative charge, and carbon does not want that negative charge, so it's trying to do anything to get rid of it. Cool. Did you guys want me to draw the mechanisms of any of these others? All of them? One of them that was particularly confusing? Just one is fine. Okay, anyone have a preference on any of these 3 or 4? We've got problem 1, 2, 3, or 4. Second one, we can do that one. Okay. So I'm going to come out and draw it over here if that's okay. Just give me a bit more space. Have potassium terbutoxide. Used to seeing that base. All right. So this is going to be E1, right? Because we have a, sorry, E2. We have a strong base. Okay, so everything here happens in one step. So our base, because we got one product here, right? It's going to steal a proton from here. Okay. And those electrons will slap down, form a double bond, and then the leaving group will leave. Basically the same mechanism, except for that it all happens in one step rather than the negative charge. Yep, exactly. So Tanner asked, are the steps in E1 and E2 the same? The only difference is that E1 has a slow and fast step. Exactly. So E1, because it happens in 2 steps, The slow step is the leaving group leaving, right? The slow step is that the leaving group kind of starts to take off, and then the base does its thing with stealing the proton. Okay, but that's the slow step and the fast step. But other than that, their mechanisms are identical. Okay. You're welcome. Is everybody okay if I move over to the elimination worksheet? Is that what you'd like me to do? Yep, okay. So let me bring it up really quickly. Did you have any specific questions on there? Or did you want me to like bring up the key and we could just talk about why certain answers are the way they are? What would you guys rather me do? Oh, you want the substitution reaction. For some reason, I was thinking you wanted the elimination reactions. You want a substitution worksheet? Okay, sorry. Let me bring up the right one then. Okay. All right, are you all able to see the substitution worksheet? Perfect. Any specific questions you had on here? Do you want me to just go over a couple of them? I'm here for you guys, whatever you need. Number 4. Okay. So here's number 4. We're going to draw the products and complete the arrow pushing mechanism for the following reaction. So because we have a weak nucleophile here, okay, how do we determine SN1 or SN2? We have a weak nucleophile, so it's going to be SN1, which means there's 2 steps, right? So first the leaving group leaves, and then you're left with the carbocation intermediate, and then your nucleophile attacks. Okay. You have your top attack where it attacks from on a wedge. You have the bottom attack where it attaches on a dash. And then the chlorine strips one of those protons away, and you're left with OCH3. Did you have a specific question on that one, Tanner? That's not making sense, or does that make sense now? The 2-step reactions are hard for me. Yeah, they're pretty tough. You just got to remember that it's first the leaving group leaves and then the nucleophile attacks after that. It does take a lot more for the mechanisms on the 2-step reactions. mechanisms are a lot longer. Any other questions? All right, so I have a question. I don't have any specific questions about anything, but what do you suggest for studying? So I would definitely use my exam review. Definitely go over the practice exam. And then outside of that, really just practice. Go through the textbook if you bought the textbook and get any examples you can. Go through all of the practice exams and make sure you understand everything. You know, he does give you a lot of resources. There's a lot of good practice problems on, you know, on Canvas, things that look very similar to the exam. So I would just focus on all of that stuff that he hands out. I wouldn't spend a whole lot of time Googling stuff because sometimes you get, you know, kind of wacko stuff, things that he doesn't expect you to know, or, you know, things like that. So I would stick to the stuff that we've provided for you. But that would be my recommendation. Go through the practice exam and any topics that you had a hard time with, go back to those sections in your notes. You know, just make sure you understand everything there. All right, and then Lynn said, when the leaving group leaves, carbocation form and the nucleophile attacks. That's exactly right. Did you have a question specifically about that? No, I'm just clarifying. Perfect. Yep. So the leaving group leaves, carbocation intermediate forms, and then the nucleophile attacks from both sides. That's what makes two products in SN1 reactions, right? Is the stereochemistry, it attacks from both the top and the bottom. If there's not a stereocenter there, then, you know, it's not gonna have two products. But if there's a stereocenter, then there will be two. Okay. Well, if there is no more questions, we will finish up there. It's been a great summer semester. Hope that I was helpful in some way and that you all are successful. Good luck on Organic Chemistry 2 for those of you that are going on. And that's it. Thanks everybody for coming. Oh, we have one more question. Group work 12. No, you're okay, Tanner. We're good. We still got time. So group work 12. Is that the elimination one? Okay. I'll pull that one up. And you're wondering about number 4. Okay. So the following E2 reaction, draw all possible products and then predict the major product. Draw the arrow pushing mechanism for the formation of the major product. Okay. So there's the answer there. Did you have a specific question? Just not sure.
Yeah. So on the di-substituted ones where there's the major and minor, so you know how the bond, one is trans and one is cis?
Yep.
Do you look at the Newman projections before the double bond forms to like, or do you just make them trans and cis for that? Like, is there a specific rule for that, or?
No, you're just gonna get both. You know that you're gonna get both the trans and cis products, and the trans product is gonna be your major.
Okay, so the chlorine, which is the leaving group, that methyl on that right side, you see what I'm saying?
Yep.
That one doesn't move, but the one on the left, that ethyl, can.
Yeah, so whatever it takes to make it cis and trans.
Okay.
Yeah, so you could move that methyl on the right side as well, but it's
As long as there's a cis and a trans.
As long as you have a cis and a trans product, exactly.
Okay.
Yep.
Awesome. That makes sense. Thank you.
No worries. Any last minute questions? I'm committed for another 27 minutes if you guys have anything.
Could you go over a practice problem for the like HNMR, CNMR, and the IR spectrum where you piece all of those together? He had a question like that on our test.
Yeah, so let's...
where you just draw the molecule after looking at all those.
Yeah. Do you want me to just pull up the exam key and we could...
If that's the only one you have, then sure.
Yeah, it'd probably take me too long to find...
Okay, no worries, yeah.
Another one. So let me get there quickly. Where did he post the exam key? Do you guys know where it's at?
I think it was on announcements. That's where I saw it. I'm not sure.
Files. He probably did post it to an announcement. Let's see. Exam 3. No, it's not in there. Okay, I'll just go to files. Exam. Let's see, key for, it's probably this one, huh? Exam 3 key. Does anybody remember what problem it was? 23. Question 23. Okay. So, yeah, sorry, I wish I could find one quickly. It'd probably take me quite a while to do it. So, use this. Okay, so what's this 2250 telling us right here? Yep, we got a triple bond, right? Most likely a C triple bond N. Okay. We have our sp2s and sp3 CHs. We have a C double bond O and a C double bond C. Okay. That's all good stuff. All right. We've got a 2H doublet and 2H doublet between 6.5 and 8. So what does that tell us? We have a di sub. We have a 3H singlet, 2H triplet, 2H triplet. Okay. There's nothing crazy going on there with as far as, you know, what we're going to see or anything like that. So let's scroll down here a little bit. Oh man, forgot it does that on here. Let's see. That stinks. Okay. Can I zoom out? No. Oh yeah, that's a beast. Was this a free response question? Man, that reminds me of the one we had, but I didn't think he'd be that mean over the summer. All right. Okay, so I guess, did you have any specific questions, Tanner, on you know, what you were looking for here, or, you know?
So I got the right answer. I just didn't know how to label the graphs really, because I was just doing it on, like, I drew all the graphs out on my scratch paper because I didn't print it out.
Mm-hmm.
But he said that to get full points, you needed to label them, and I wasn't sure how to label them, so I wrote by like every peak and everything, C double bond or C triple bond N, and then I wrote whatever all the HNMR hydrogens meant. But the carbon one, the CNMR, I didn't really know how to label that one mostly.
Yeah, so it's mostly just like you just choose, like he shows here that he went through each different type of carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Then he went to the CNMR graph and he said, okay, you know, which of these peaks is going to be these carbons, and it is very confusing. But if you have the chart he gives you, he'll say like, you know, a C triple bond N is going to show up somewhere around, you know, 118 or something like that. So you'd say, okay, that's my carbon 1, right? And then he'd say, well, you know, you just kind of work through it like that. Does that make sense?
Yeah, that does. So he just matched whichever peak to the carbon, and then the peaks on the hydrogens to the hydrogens.
Yeah, and then the 4, 5, 6, 7, they're really hard to differentiate between as far as the carbons on a benzene ring. So he knew those were your 4 carbons there, but he didn't make you specify which. Yeah, okay. I'm sure if you tried your best, then he would have given you full credit. But I know it's kind of tough. We didn't go over that in my exam review, and I didn't know he was going to be that mean to you guys. I apologize.
No worries. So yeah, I mean, I got the molecule right. I just didn't know what he really meant by labeling everything. Yeah. So that makes sense, though.
It makes more sense now.
Yeah.
Yep. Cool.
Well, thanks for last minute questions.
Oh, of course.
I don't have anything else. I'm just trying to think of things to make you do.
No, you're good. I mean, anything
practice,
helps. So. Yeah, anything helps.
Okay.
I could do one more elimination reaction for you guys if you want to, or we can call it quits. How are you feeling?
I'm pretty good with those. I don't know if she wants to do them, but
oh no, I'm good.
You good?
Yeah, can we just go back to this question, because I had them switched around. I don't know why I did that, but I had that I guess where the number 9 carbon is.
Mm-hmm.
I had just that to a regular O, a single bond to O, then the benzene ring. And I put I had the triple bond like internally because I thought there was a signal for that. If it was terminal.
Signal, yeah, that's the terminal signal right there.
Oh, okay. I thought
So if it's not terminal, then it doesn't show up right there. But that's a nitrogen, so it will always show up, right?
Oh, yes. Okay. I thought there was another signal for it somewhere else, but well, I don't know.
So it always shows up in the 2200-ish region, triple bonds. If it's a C triple bond N, it'll always show up. If it's a C triple bond C, it'll only show up if it's terminal. If it's an internal alkyne or triple bond, then it won't show up there. And that's what makes those tricky. But he was kind enough to give you a C triple bond N, so you knew it was on the end.
So why does it show up as terminal if it's like that? But because if you have the peak, it's like 3300. I don't know. I don't have the sheet in front of me, but
yeah,
that would be an sp hybridized hydrogen. So if it doesn't have the peak in the middle, does that make sense?
Yeah. So are you saying like the fact that if it's terminal, you also get this sp hybridized CH?
Yeah. But if it's internal and it doesn't have the peak in the middle and it still has the sp hybridized CH bond, like, does it have that?
No, it won't have that.
It won't have that. Oh, okay.
Yeah. So I'm not sure why that doesn't show up. I mean, it's hard to really know. I mean, I'm not I'm not an organic chemist or anything as far as like why things show up and why they don't, you know, but I just know what to look for in the peaks. And I just know that if it's an internal, it doesn't actually show up on IR at all. That's where like your HNMR will come in to tell you, okay, well, something's going on here where I know there's more carbons, but you kind of just have to piece it all together. It's really confusing sometimes. This actually reminds me a lot of what we had on our exam when I was in OChem 1, this structure. I think he gave us the mass spec as well, though, which helped a little bit.
That would have helped. I think he meant to give us that instead of, because he didn't really go over the carbon one as far as like numbering it.
Labeling them.
Yeah.
Yeah.
Well, I don't remember, but.
Yeah. Well, and the mass specs helps because then you can say, okay, do I have all the double bonds that I needed? Did I have all the different pieces and stuff? That's tough. Yeah, that's really tough. I'm sorry, guys.
That one was pretty
Tough
wicked.
question.
It was.
But anyway. All right. Well, if you guys don't have any more questions, we can call it.
All right. Sounds good.
Thanks for coming. Great semester, and good luck on your final.
Thank you.
We'll see you guys around.